Afternoon, everybody. I'm Anthony Weaver. I'm a graduate student here. I'm currently working with Dr. Aruzazari. And we've been performing nanoindentation studies of silicon carbide. So we Stan Tiago got a plate of silicon carbide from ARL, and due to some concern he had over plate to plate differences, he gave me half of his plate. I was able to take it to the machine shop and get two samples cut off, about 3mm by 9, just small samples. I ended up having two samples, that way I could polish two different orientations without having to reuse the same sample again. And go through the trouble of remounting it and reprocessing it. So our first sample is in the ND orientation, and our second sample would be in the RD or TD orientation. One of our main assumptions is that all of the mechanical properties in either the TD or RD direction should be equivalent. So we performed quasi-static indentation with the Brooker TI-980 indenter with their new MRNP maximum 2 Newton multiprobe transducer with a Berkovich diamond indenter tip. I set it up for a maximum load of 50 millinewtons with a both loading and unloading rate of half a millinewton a second, and a hold time. At the beginning, we did a hold time of 2 seconds, but after some concern about whether or not that was long enough for any I guess deformation to actually happen, we extended it to 5 seconds. So our initial nanoindentation results pointed towards the material being very anisotropic, almost to the tune of a 2-to-1 ratio of RD to ND, RD to the ND face. But these were only 2 trials, 2 indentation sets. We ended up doing a simple grid indentation of a total of 20 indentations per trial. So it was so very surface level, didn't do a whole lot of indentation. There was some talk about the possibility of a gradient of strength, a strength gradient from the top to the bottom of the plate during the cooling process. So to investigate that possible phenomenon, I went ahead and did a profile of the RD or TD face, and just did a single line of indentations from one edge all the way across to the other. And we found that there was pretty much no trend whatsoever. It pretty much remained on average between 350 and 450 gigapascals. So one thing that we noticed is that per indent, some of the data was, for lack of a better phrase, a bit erratic. And so after thinking that, or we also discovered that we also saw a pop-in phenomenon with indentations, and thought that it might be this surface actually cracking. So I looked at it under optical microscope, and found that for whatever reason, the surface had become pitted and quite worn. So I decided it was a good time to polish it, especially now since we had recently gotten our parallel fixture auto polisher. And so I ended up polishing it from 9 micron all the way down to 1 micron, conforming to the rule of thirds. And I found that previously when we had polished samples, we were polishing them just by freehand. And that actually introduced a sloped surface that we ended up testing on. And each surface had about 100 to 120 micron height difference edge to edge, which at the nanoscale can have a lot of impact. And so to further investigate the possibility of cracking with my load, my maximum load 50 millinewtons, we did some SPM imaging. And so with the MRNP high load physio, I went ahead and did my single indent of my standard load function. And then I came back with the low load cell and performed SPM imaging of a 5 micron by 5 micron scan area. And as the figure with detail, we can't see any large cracks or large deformations. Recently, since we went ahead and repolished, I went ahead and did a full set of testing. I ended up keeping the simple grid batches of 20 indentations, and we did a total of 160 indentations on the larger RD phase, and then a total of 100 on the ND phase for a grand total of 260 indentations. With the ND phase, we found that regardless of location on the ND phase, it seems to be very consistent and not ranging a whole lot, but as far as the TD phase, depending upon location, it could vary quite wildly. And with positions 1, 2, 3, 4, 5, and 6, they were more consistent. 7 and 8, for an unknown reason, ended up being more erratic than the rest. So in summary, we went ahead and performed indentation, maximum 50 millinewtons. It should not lead to cracking, and most of the literature supports this, as most literature saw cracking only upwards of 100 millinewton loads. For the RD phase, the elastic modulus varies significantly depending upon the indentation location, ranging from as low as 250, about 250 to 360 GPa, while the ND phase is more consistent, and larger deviation of hardness values is also present in the RD phase. And then we're looking into a plausible explanation for this being possibly part of the process without the manufacturing, but we're also looking into porosity as well. We're looking into performing electron microscopy to see if there are any really fine cracks. We're also going to create additional specimens, particularly from the very middle of the plate, to see if there's any differences from middle to edge of the plate. And then, of course, we're also going to go through and do EBSD just to look at the crystal structure, and then we're thinking about intentionally inducing cracks through nanoindentation to evaluate the fracture types. That's it.
Do we know anything about how these samples were manufactured? Other than anything about?
Yes, so we first assumed that they had done it through, I believe it was like a hot pressing, since it's such a simple shape. But I think in an email a while back, ARL said that they had manufactured them through pressure sintering.
So pressure was. Do we know these are cubic phase or hexagonal phase?
Hexagonal. They are the crystal structure is a mix of 4H and 6H silicon carbide.
So you would expect it to be very anisotropic.
Yes.
And right, still though, like their lathes usually.
Would you expect a significant difference in the properties between the two molecules you have?
That I do not know. I've continued looking into it, but unfortunately, there's not a whole lot out there on specifically 4H and 6H. Especially when you look at polycrystalline, because there's a couple of things on how they differ in single crystal, but not necessarily anything that's too close to this exact situation.
In reference, we do have single crystals of 4H and 6H if you want to test them.
Oh. That'd be interesting.
And Stan's gonna talk more about this shortly. Thank you very much.